Okay, our next section, 3.7, is called Recursive Formulas for Arithmetic Sequences. Now, you should say that in your mind, recursive sequences or formulas sound familiar. We have dealt with those back in Chapter 1. The arithmetic sequence is something new, but we'll explain that as we move forward. We've also had back in Chapter 1 an explicit, but that'll be coming in Section 3.8. So think we're going to use the recursive form and the recursive form only right now to help us through our work. So give me a second here and we will move to our first slide. All right. If I asked you how can these shapes be arranged in a sequence, we want to start thinking sequences again. And there's lots of different sequences out there in math. But we're going to be today focusing on recursive sequences. But before we do that, here's a little fun. Maybe some of you in this situation would say, oh, I would rearrange these shapes. Let's say, oh, this guy first, this guy second. Oops. So that it would be like this. And in doing so, you probably went from most shaded to least shaded. Some of you may have went the other way. Those are typical ways to arrange those triangles in a sequence. Again, sequences. How can these ones be arranged in a sequence? So look at those. Decide how you would arrange those. And probably in class, we're going to ask somebody to come up and put their sequence up here. So look at your choices and see what you would do. Next one we need you to think about are several. Well, let's do them one at a time here. So if you can find a pattern to each of these numbers, because these happen to be number sets, and we're going to be working more with number sets as we move forward. So if you looked at this blue one, set of numbers, 2, 4, 6, 8, most of you should be able to come up with a pattern. What is going on in this series of numbers? Got yours? Most people say it was an add 2, add 2, add 2. Next one. Numbers go 1, 2, 4, 8. What is your pattern that you see established? Can you find a pattern in this set of numbers? Again, that pattern is a times by 2. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. The next number, 8 times 2, would give us a 16 in that pattern. Next one. A negative 64, a negative 16, a negative 4, a negative 1, a negative 1/4, etc. What do you see on that one? In this case, we're saying it's a divide by 4. A negative 64 divided by 4 is negative 16. Negative 16 divided by 4 is negative 4. Negative 4 divided by 4 is negative 1, etc. 1, 1, 2, 3, 5, 8, 13 is the number pattern this time. So look at that. One strange or new piece is you have repetition in this one, but you also have a pattern. If you can't see it right away, we should hopefully be able to say we're adding the previous terms. So if you take 1 and 1, add them together, you should have gotten 2. Then 1 plus 2 should have gotten you 3. 2 plus 3 is 5. 3 plus 5 is 8. So the two previous terms add together to get the next term in the sequence. And our last one, 1, 2, 4, 7, 11, 16, 22. again, a series of numbers that is in a pattern. What do you believe that pattern is? This one is add consecutive integers. What does that mean? Well, if I added 1 plus 1 here, I would get the 2. If I added 2 next, I would get the 4. If I added a 3 next, I would get the 7, etc., etc. These are your consecutive integers. 1, 2, 3, 4, 5 would be the next number. And 11 plus 5 is 16. And you go right from there. So you're adding consecutive integers. Those are all patterns. A couple of them could be patterns that we discussed today. But remember, that's what a sequence is. A sequence is a pattern of numbers. So to be specific, in our sequence that we're going to use today, we want you to think of, even in nature, there's lots of numbers. And Fibonacci's sequence was one of them that was listed in our list there. And these are all places in nature where you see what was called Fibonacci's sequence. You have coral, you have a winding staircase, sunflower, the inside view looking down of a flower petal with its stems, a snail shell, a snowflake, and inside of a seashell. These are all natural occurring sequences in nature using what we call Fibonacci sequence. But our sequence today is not going to be as difficult. Ours is going to be what makes a sequence arithmetic. And you've already read, so you should know that a sequence is arithmetic because of the word arithmetic, which is a simple and quick, easy way to say arithmetic. So what makes it arithmetic? If it goes up by a constant number, that's arithmetic, or it goes down, subtracting by a constant number. Here is the definition of a recursive arithmetic sequence. Recursive, remember, it has to have those two pieces to the equation. That makes it recursive. But when we say it has to have those two pieces, we're talking that first line. Actually need a better color here. So let's go white again. That first line and that second line, recursive. So you're going to recur. And also a piece of that recursive is this feature right here. What did we say a sub n minus 1 was back in chapter 1? Hopefully you just said it stands for the previous term. So again, when I read this, I'm not going to read it. I'll read it poorly the first time. I'm not going to read it. A sub 1 equals my number. A sub n equals a sub n minus 1 plus d for n greater than 1. We'd like you to read it for meaning, which in this case actually means my first term is whatever that number is. All other terms in my sequence, remember that came from a sub n and this for statement going together. When I put those together, that means really I'm calculating the second term, the third term, fourth term, fifth term, sixth term of the sequence. So all other terms of the sequence will be calculated by taking the previous term plus d, d being that constant difference between the numbers. There will be a constant difference between all numbers in our sequence. So if you haven't, you saw it in the notes, you've now seen it here in my lecture, memorize this. A sub 1 equals your number, a sub n equals your previous term plus that constant difference for all terms in your sequence. What is the sequence that's generated by this statement? So we're looking for, what is the sequence? How many terms do we have? As you read it for meaning, you can say, my first term is 53. And if your first term is 53, then you write 53, comma, get ready for your next one. You have to generate it, though. All other terms in my sequence will be calculated by taking the previous term, subtract 7. And so I've now told myself what I need to do, and here I go. 53 take away 7 is 46. 46 take away 7 is 39. 39 take away 7 is 32, etc., etc., depending on how many terms they ask you to generate. Okay? So, given a recursive arithmetic formula, sentence, whatever you'd like to call that, you should be able to generate the sequence. Or the other way around, consider, here's your sequence, now you give me the recursive formula. So, get ready to write. We know it's a two-termed sequence equation. And we look at what we have first, do a little calculating. I see, 112 to 120, so it's going up. And what'd you say? Well, it's going up by 8. 120 to 128, going up again by 8. So you can say plus 8, however you want to do that. 128 to 136, again, we've got going up by plus 8. So I think we've found our constant difference. We also have our first term here, so I think we're ready to write. Let's go. What variables you use is up to you. They were using A's for arithmetic sequence. I think I'll stick with that, but you could use anything as long as you're consistent. So A sub 1 equals 112. All other terms in my sequence are going to be calculated by taking the previous term, A sub n minus 1, and adding 8 in this case. And I already included for all other terms, so now all I have to do is just state that for statement. For my n value here has to be, you have to say either greater than or equal to 2, or you could have said n is greater than 1. They basically both give you the numbers 2, 3, 4, 5, 6, which is what we need in this situation. So recursive has to have that two-step process. Recursive formula has to have that for statement. And we've got it. And so it's looking pretty good. All right. Knowing that, you should be able to go back and forth and do exactly what we did here. Take a recursive arithmetic sequence, write it as a formula, or take a recursive arithmetic formula and write it as a sequence. The more practice you get, the better you'll be.